So we have seen that the particle will perform oscillatory motion in the case of only a stable equilibrium position. So it is important. So if you plot this stable equilibrium position, then we know that the net force is going to 0. So if net force on the system is 0, then you can write this net force as a del upon del x. So this is equal to 0. Now most important thing is that if del upon del x, you know that this position can be the position of maximum or the position of minimum. So this indicates that u can be minimum or u can be maximum. So u can be minimum or u can be maximum. But for oscillatory motion, we have seen that we must have to satisfy the condition of minimum. If the curve is like this, then the particle is going to perform oscillatory motion. So from induction, we understand that if you do the double derivative of this kind of potential, del upon del x square, then it is going to remain negative. So if this condition is going to satisfy, then particle will be in oscillatory motion. So these are some mathematical conditions to perform a particle in oscillatory motion. If you plot this, then you will get this kind of curve. U as a function of x. Then this curve will be like this kind of curve. So this is okay. Now our main is to understand one more important thing, that is a condition for oscillatory motion. What is the condition for oscillatory motion? Condition for oscillatory motion. What is some fundamental condition for oscillatory motion? So main thing is that suppose the particle is performing oscillatory motion in this region. This is some fixed point. So if particle is displaced in this direction, then the force must be acting in this direction. Otherwise this is not going to perform oscillatory motion. So if you displace the particle in that, so if you displace this particle in this direction, the force must be acting in this. Yeah? Then particle is going to come back. Otherwise the particle is not going to come back. So the mathematical condition is something like this: force must be equal to minus of displacement. And this displacement can be here I don't know any kind of power, but in general case, if you talk about general case, then this power is going to end. But if you impart some mathematical condition, then you are going to get, suppose if any even is 0, 2, 4, 6, in that scenario we are not going to get oscillatory motion, because if any is even, then suppose if any is even, then what is not going to happen? This is because if any is even, then suppose this person is negative, that means particle in this region. So if x is negative, then if you compute the force, then the force is positive. That means force is also in this direction. So the displacement is also in this direction, and the force is also in this direction. So in that case, the particle is not going to come back. So there is no any kind of oscillatory motion in this thing. So if n is odd, that is going to satisfy the condition of oscillatory motion. So if n is odd means 1, 3, 5, 7, kind of this kind of thing, then we are going to get the oscillatory motion. Now if you put n equal to 1, in that case we are going to get a simple oscillation, that is simple harmonic motion. So f is equal, and if you remove this proportional constant, then you are going to getting some k kind of thing, and that's this is basic equation of force SHL. So this must be satisfied to perform simple harmonic motion. Now we know from Newton's law, this is basically net force on the system. So net force on the system must be in this behavior to perform oscillatory motion. From Newton's law we know that net force is nothing but mass times acceleration. We can write this net force as mass times acceleration, and it is equal to minus of kx. Now my aim is to calculate acceleration from here. Now if you calculate acceleration, this will be nothing but k upon m into x. Here k is also some kind of constant and m is also some kind of constant. So we are going to replace this k by m with another constant and it is known as omega angular frequency. We'll see that what is angular frequency in next session. So this is k upon m. This is what k upon m. This is called as omega square. So if you calculate acceleration, this will come like minus omega square x. So this is the most important condition. If you are going to satisfy the acceleration of the particle at minus omega square x, then this particle will be in simple harmonic motion. So in class 12 or in any problem of SHM, if you are going to satisfy these two conditions, then the particle will be in a simple harmonic motion. Now if you plot, suppose if I plot this curve, then this curve will plot this curve of SHM, then this curve will be like some straight line. Because it is equation of y equal to mx. Y equal to mx. And this is basically theta, it is equal to theta. Suppose this is the stable position from where the particle is coming back. So if you calculate, we know the slope of this tan theta. So if you calculate acceleration, this, or suppose we calculate the slope, this is nothing but tan theta and it is equal to omega square. That is the most important thing. This kind of a graph you can get. Suppose you have given this kind of graph and ask the slope, so you have to solve using distance. This is a basic straight line equation. Now our aim is to develop the basically what we have seen here in oscillating motion or oscillating kind of motion. Everything is repeating after an interval. So we are seeing that suppose at some time the particle is here, and after some time the particle will going in this direction, and after some time the particle will going in this direction. So what we have seen, the position, velocity and acceleration all have basically are starting varying with time, position and everything. So our aim is to calculate the position as a function of time, the velocity as a function of time, and acceleration as a function of time, because everything is a function of time. So our next aim is to develop some kind of equation. So this acceleration, we know that we can write this acceleration as d2x upon dt square. So if I write this acceleration as d2x upon dt square, and this is equal to minus omega square. So we can write also this is d2x upon dt square plus omega square x, and this is equal to 0. This is basically fundamental equation of simple harmonic motion, and this is differential equation of second order. We are going to see the order is second. So the solution of this equation is beyond the scope of IDAC. But the thing is that you are going to see this equation at many times, in many intervals. So we are going to develop a solution for this equation. We are going to prove this with the help of physics. But for this time we are going to just learn or remember the equation. If you solve this, then we are going to get x something like a sine omega t plus pi. This is the solution of this equation. We have to remember this. I am going to solve with using some concept. So one of the most important things. Now this is the position of function of time we will calculate. If I differentiate it, suppose we know that velocity, if our aim is to get velocity as a function of time, then I will going to differentiate this. That is velocity nothing but we know that velocity is dx upon dt. So if you differentiate then we will get e omega cos of omega t plus phi. Simple. And if I calculate acceleration from there, then acceleration will be nothing but d2x upon dt square. And if you calculate here from here, we are going to get omega will come more, and for cos we are getting a negation. So this is something like omega square kind of thing. A sine omega t plus phi. Or we can also write this as minus omega square x. That is same thing. This is basically position as a function of time. This is a velocity as a function of time. This is acceleration as a function of time. These three equations will help you to understand mechanics in simple harmonic motion. Now, my main is to basically plot some curve. Now, suppose I want to. So before plotting the curve, we are going to understand some dynamics of simple harmonic motion. Okay. So what is going to happen, and how the motion is basically proceeding in the case of So, so the main thing is that how the motion is occurring. Suppose we have some kind of oscillatory motion or simple harmonic motion that is between plus minus and this is mean position. So our first aim is to illustrate the dynamics. Then we are going to proceed further. So what is happening here? This is mean position. Now we know that the particle is going up that region and from there the particle is coming back. So that means in the kinematics you have done the particle is moving in a straight line and it is turning back. That means at which point he is getting to turn. At that point the velocity of particle must be zero. So at this point the velocity should be zero. So from here particle is also turning back. So at this point the velocity should be zero. And we know that in oscillatory kind of motion the force is basically proportional to displacement. So here the displacement is maximum. So force should be maximum here. If force is maximum, then acceleration should be maximum here. So same condition here, acceleration should be maximum here. But force is maximum. And at this point, suppose for the particle come toward the mean position. Then at point the force is also in this direction. So acceleration will also in this direction. So velocity is also in this direction. So speed is varying. That means when particle is going to come at mean position, the speed will have the maximum speed. So what was at that point basically as is zero. That means acceleration is zero. So what we have seen that at extreme position the force is maximum, the acceleration is maximum, and at mean position what we are going to see that the velocity is maximum. So we can also calculate that if velocity is maximum here, that means the kinetic energy is going to be maximum. Okay, we will see that in when we deal with the kinetic energy and potential energy. Now the main thing is that what is this extreme position plus A or minus A? Because it is very important. We are going to see a lot of many times this plus or minus A. This plus A is known as amplitude. This is amplitude. What is the meaning of this amplitude? We can define this amplitude as basically two times. So what is amplitude? Amplitude is basically the separation between mean position and extremum. So you can see that this is the separation between minimum or extremum or mean position. We can also define this as the half of the separation between two extremum positions. Okay, in some equation. So we can write also. This is some kind of distance. So it will be during equation the meter, and it will write the dimension. Then it will be measurement. So now I am basically concluding this lecture at that moment. In next class we are going to learn about some plot of this A and B curve at position at the first time, and many things we are going to do in